Good evening, everybody. Today we meet once again to hear some really interesting information. Today's webinar on waterless dyeing is going to help us witness the future of sustainable dyeing with Deven Supercriticals India. And Dr. Swapneshu Baser is going to give us an insight on what are the supercritical fluid processing technologies and a lot more. So Suprona, no, waterless dyeing of all textiles using conventional dyes. Let me give you a little background to that. Today, it is a very important for textile materials, even those using recycled raw materials, to use truly sustainable technologies during processes like dyeing and finishing to achieve end-to-end sustainability. Thus, there is need for dyeing and finishing technology, which is genuinely capable of saving on all three aspects, that is hazardous chemicals, energy, and water. It is with this regard that Deven Supercriticals India has developed and internationally patented an innovative, waterless, sustainable, single-step dyeing and finishing technology, Suprono, which meets above requirement for man-made as well as natural textiles. Now, all the above features result in substantial reduction in overall chemical pollution, water and energy load for processing all types of textiles using single machine, making Suprono a truly revolutionary Atmanirbhar technology from India for the world. And with this, let me introduce you to Dr. Swapneshu Baser. Is a chemical engineer with MTech in Polymer Science and Engineering from IIT Delhi and PhD in Chemical Engineering from IIT Mumbai. He also served as Adjunct Associate Professor at the Department of Chemical Engineering, IIT Bombay, till 2006. He is the founder and managing director of Deven Supercriticals Private Limited and has played a major role in design, development, implementation of supercritical fluid processing technology through his association with IIT Bombay and subsequently with Deven Supercriticals. Dr. Baser has been granted 3 international patents in USA, Europe, and India related to various aspects of SCF technology, including sustainable dyeing of textiles, trademarked as Suprono. May I now invite Dr. Baser to please present all your findings about your product. Welcome, sir.
Thank you. Thank you very much, Professor Deven. And thank you very much, Nisti, Dr. Lal, and Dr. Yadav for your kind arrangement for giving us an opportunity to talk about our indigenous technology on the eve of our Independence Day on 14th of August. And basically, I welcome all, and we'll be today talking about our indigenous technology as discussed, that which is an improved version of use of supercritical carbon dioxide for dyeing and finishing of textiles. Our company, as it was just told, it's called Deven Supercriticals. So as you can see from our title, it is having supercriticals in its name. So we have been dedicated in the area of supercritical fluid commercially for last 25 years. And on research front, I have personally been involved for last 30 years doing supercritical fluid processing applications and turnkey projects. So Deven Supercriticals is an innovation-driven company dedicated to world-class supercritical fluid processing for more than 2 decades. And we are a spin-off company out of IIT Bombay, established in 1998. And we offer turnkey projects from pilot to commercial scale for various applications of supercritical fluids. In last 25 years, we have supplied around 26 plants from small to big, and in India and abroad, even to Europe on commercial scale for other applications of supercritical fluids. And we have, as said by Professor Nian, that we have been granted a few international patents on different aspects of supercritical fluids, and dyeing of textiles is one of them. So I'm really happy to share with you today our work in the area of dyeing of textiles in a sustainable way. And basically, we really need to focus on sustainability with a very wide and overall scanning, because today when we talk about sustainability, typically people talk about water and energy. No doubt water and energy are important, but also the chemicals used in the process are actually playing a bigger role in affecting the sustainability of the environment as well as the humans and animals. So unless we have all three aspects, that is the hazardous chemicals, water and energy being audited for any given application, the sustainability may not be complete. So as we know that the chemicals typically when they are getting produced at that stage at the origin also produce a lot of pollution. During their transportation, there is an issue. During handling at the end user and then subsequent disposal, again, there is a lot of pollution issue. So the bad name for the chemical industry and the textile industry comes more with the chemicals than water, because with water, you can have zero liquid discharge technology and recycle most of the water. Energy also, you can tend to go for more environmental energies like wind energy, solar energy, and so on. But for chemicals, there is no substitute as such, which can be universally applied. And that is where our technology Supra Uno is really having a edge over the other technologies available in the world. So basically, we know that whatever chemicals we are going to use in our process ultimately will find their way in the wastewater and then ultimately in the soil. And the moment they go to the soil, it's an irreversible process, and it becomes a main problem in long-term health of the people around in that area. So we should actually have better legislation, which is happening, that we are having more and more stringent pollution control norms every year. Also, the cost of water and wastewater treatment to meet the pollution control norms is increasing. Cost of energy is increasing. So basically, we really need to work on all three aspects. And supercritical fluids is one of the contenders to actually replace water and also to save on energy and chemicals. So basically, supercritical fluid can be any material above its critical pressure and temperature. And here we are talking about carbon dioxide. So why we are talking about carbon dioxide is because at supercritical state also, it will have very high rate of diffusion. It will be able to penetrate very quickly into the textile, and that will actually significantly reduce the dyeing and processing time. And as we know, carbon dioxide is non-explosive, non-flammable, and so it is termed as generally regarded as safe. It's a GRAS solvent. And CO2, as we know, is inert. It doesn't react easily with any material. So it will not be damaging the textiles as well as the chemicals which are used along with carbon dioxide in the process. And we all know that carbon dioxide is termed as a greenhouse gas. But carbon dioxide, which is going to be used for our process, is not going to be produced for application in our process. That is, we are going to use the carbon dioxide, which will be produced anyway as a byproduct from some other bigger processes like urea production or fermentation or bio-CNG production, has carbon dioxide as a major byproduct. And till now, people used to use that carbon dioxide, which is a byproduct, for other applications like carbonated drinks like Pepsi and Coke. To carbonize, they used to use the carbon dioxide after purification. So since the bottling plants are there at many locations near the cities of tier 1, tier 2, the logistics of carbon dioxide, liquid carbon dioxide being transported and made available at a food grade level is very well developed. And the same food grade liquid carbon dioxide will be the raw material for us. So in effect, we will become carbon dioxide neutral, because the carbon dioxide was anyway getting produced and was to go to the atmosphere. We are just recycling it in our process. So we are not generating additional carbon dioxide for our process. This particular diagram here, we are showing the 3 phases of material: the solid phase, liquid phase, and gaseous phase. And as we know that any gas, when we start increasing the pressure, this is the vapor liquid equilibrium. So when we cross the vapor liquid equilibrium with increasing pressure, the molecules will start coming closer to each other to bring gaseous phase into liquid phase. And the significance of this critical temperature is that the moment we start increasing the temperature of a gas, what we are doing is we are giving more thermal energy to the molecules. So the molecules will vibrate more. And beyond this particular critical temperature, the energy, the thermal energy provided to the molecules is high enough so that no matter how much you increase the pressure, actually the molecules will have energy to resist coming very close to each other to form a liquid phase. But because we are increasing the pressure, the molecules will be becoming more and more compact. And in loose terms, we can say that at supercritical region, which is above critical temperature and above critical pressure, we will have something like a high density gas. So because of the higher density, you will actually have the supercritical fluid to have solubility like a liquid. But because it is not liquid, it is more like a gas, it will actually have properties to penetrate and flow like a gas. It will have a very low surface tension. So you have a win-win situation. You have a fluid which can dissolve like a liquid, but flow like a gas, will have much less pressure drop, much better penetration. So that's a real advantageous situation. Now for carbon dioxide, this is the pressure temperature diagram again, where we can see that the critical point is defined by critical pressure of 74 bars and critical temperature of 31 degrees Celsius. So above 31 degrees Celsius and above 74 bars, or typically 74 atmospheres, this particular yellow box represents the supercritical region. Now you can see that by small change in temperature and pressure, we are able to change the properties of this carbon dioxide in supercritical state in a very dynamic way. So right from 200 kg per meter cube to 900 kg per meter cube kind of density can be changed by change in temperature and pressure, or 0.2 gram per cc to 0.9 gram per cc. And this good amount of change in the property of the supercritical fluid by selecting the correct pressure and temperature will give rise for different applications, suitability of carbon dioxide to be used in supercritical state for various applications as a medium. And when we actually are today going to talk about dyeing application with supercritical carbon dioxide, let me first introduce to you the prior art technology, the technology which is present in the world today. Before our innovation came in, this particular flow diagram here represents the prior art technology which was available in the world. And let me tell you that even in 1997, in Germany, I had visited one trade fair called ACHEMA in Frankfurt. So even in 97, the same kind of prior art technology was demonstrated at ACHEMA by a German company with a working pilot scale plant, where they were talking about the same concept and only possibility to dye polyester and use of special dyes and also on, which till recently was being talked about as a limitation. And that's where we have come out with a innovative solution and trying to remove the limitations from the prior art process. But just to give you an idea about what was involved in the prior art process is, now we need to go to the supercritical state by increasing the pressure. So we use the pump to increase the pressure above critical pressure, and then we use a heat exchanger to increase the temperature of this high pressure liquid CO2 to have carbon dioxide above its critical pressure and temperature as a medium or a solvent for us. Now we need to use supercritical carbon dioxide to dissolve the dye. So the dye to be used for dyeing is kept in the area which is called dye dissolution area. So the supercritical CO2 as a solvent will flow through the dye, will dissolve the dye based on the solubility, and that particular solvent solute mixture of dye in supercritical CO2 will be made to flow through the dyeing vessel. And in the dyeing vessel, we'll keep the fabric or the textile to be dyed. And when supercritical CO2 with the dye will go through the textile, it will pick up the dye based on its affinity for the dye, and any unused dye will come out along with the supercritical CO2. Then we reduce the pressure and temperature below the critical pressure and temperature so that any unused dye can precipitate out. The solubility goes down when you come below the pressure and critical pressure and temperature, and pure carbon dioxide is recycled back. So every time supercritical CO2 goes through the dye dissolution area, dissolves the dye and puts that dye onto the fabric till you actually build up the shade every time by putting small amount of dye. So the limitation here was that whatever dye typically we use in the world today was developed for water as a medium. And as we know that water is a polar solvent and carbon dioxide is a non-polar material. So whatever was dissolving or solubilizing in polar water molecules with polar water molecules will not dissolve as efficiently with carbon dioxide, which is non-polar, and at supercritical conditions it can be partially polar, but still the solubility will be very low. At the same time, the amount of dye required for dyeing of any amount of textile will be much smaller. So when you have a small quantity of dye in the dye dissolution area and supercritical CO2 is passing through the material, the contact time between the dye and the supercritical CO2 will be very limited. At the same time, the contact area also is going to be very limited because of the less quantity of the dye. So all three factors of having low solubility to start with, to have less contact area and to have less residence time will result in a very, very dilute solution of the dye in supercritical CO2. So when it is going to flow through the textile, and even if the textile has a good affinity for the dye, it will be able to take only small amount of dye at every pass. And it will take longer time for you to dissolve the dye, take it to the fabric and build the shade onto the fabric. At the same time, in real life, we actually don't use single color. We use trichrome recipe to develop a shade by having a particular combination of yellow, red and blue colors so as to have the flexibility to achieve required shade. And with that trichrome recipe, once you have three colors, which is yellow, red and blue, each color is different only because its chemical structure is different, right? So when the chemical structure is different, the solubility also is going to differ. So even if you mix the three colors in the dye dissolution area, whatever is having higher solubility will tend to come out first, and it will lead to the second most soluble material and then the third one. So because of this discrimination in solubility, you will not ultimately get the same composition of the trichrome onto the textile, and you may not be able to get the correct shade as you were looking for by mixing it in a particular proportion. And for that reason, the prior art technology even till today uses special dyes. So for every shade, almost they have to get a special dye made, a single component dye made, which can then flow through the dyeing vessel and give that particular shade. So it becomes very, very difficult for us to or very expensive and long process to get special dyes from the dye manufacturers for every shade. Also, basically, we can have some kind of a uneven flow. When the carbon dioxide is going to flow through the bulk of material in the dyeing vessel, it is possible that you may have uneven path of resistance, so that uneven flow may take place, which is called channeling typically. And if you have channeling, you may actually get some kind of uneven dyeing. So all these factors put together, and it was only possible for dispersed dyes and for polyester. So all these three factors were making the technology less versatile, slow, and less efficient. So basically, this is where we actually got an innovative idea, and which actually we are able to use for removing the kind of limitations I talked about. So basically, you can see on the left side a prototype plant which we have at Mumbai for doing trials for the industry. And in last 3 years, we have done more than 1,000 trials for the industry using the same fabric which they use, the conventional dyes which they use, but without water, without salt, etc., which I'll explain in next slides. And this is a commercial scale plant which we make for different applications. And with our innovation, we are able to use the similar other application plants for dyeing also, so that actually our experience of last 25 years of supplying commercial scale plants, where our oldest commercial scale plant is running for last 22 years continuously in 3 shifts, is very much useful in textile dyeing application also. So what we do differently as compared to the prior art, I can explain in this particular diagram here, where what if you can imagine the analogy between sugar. If you take a chunk of sugar and put it in water, it will take some amount of time for the whole sugar to dissolve in water and lot of stirring. Whereas if you take the sugar and powder it and put it in water, it will dissolve instantaneously. So by powdering, what we have done is we have increased the surface area of the sugar tremendously. And then the interaction between the water, which is solvent molecules, and the sugar molecules, which is the solute, increases tremendously. So then you get instantaneous dissolution of the solute into the solvent. So now with our improvement or our innovation, for which we have received patents, we actually are increasing the surface area of the dye onto the entire textile before it is getting exposed to supercritical carbon dioxide. So earlier it was getting dissolved at one place and then taken to the textile and giving rise to very slow process. Here what we do is we take the dye and spread that dye onto the entire surface of the fabric which is to be dyed in a particular concentration which is required to achieve a particular shade of the dye. So now we can make a solution of the dye and spread it onto the entire surface of the fabric as a pre-treatment, and then we actually dry the material so that the dye is present in a very thin layer and in a given concentration, uniform concentration on the entire surface. And when we expose this particular pre-coated fabric to the supercritical carbon dioxide in the dyeing vessel, what happens is the instantaneous dissolution will take place because of very high interaction, very high surface area, and the dye will get penetrated inside the textile at every surface, because at every surface you have the equal amount of dye, which doesn't have to now travel from dye dissolution area to the textile. It's already there on the surface and it actually gets penetrated inside. And by doing this, we actually have been able to remove the limitations of the prior art technology, which is available with the other countries and other suppliers. So our Supra Uno process actually can now be used for dyeing of polyester as it was done before. But apart from that, we can now dye cotton, linen, flax, viscose, polyester cotton, polyester viscose blends, nylon, acrylic, wool, etc. without using water with supercritical CO2, and we can use the respective dye. That means for polyester we can use disperse dye, for cellulose we can use reactive and direct dye, for nylon we can use acid dye, for acrylic we can use cationic or basic dye, which is the conventional dye, and we can also use the prior art trichrome recipe. Like for example, for our exhaust process or soft flow process, or for continuous process with water, whatever trichrome recipe we are using with the conventional dyes, we can use similar trichrome recipe with the same dyes and do dyeing without using water with supercritical CO2 by using our Supra Uno process. So we have been able to achieve now very good solubility of the conventional dyes in supercritical CO2. We have better efficiency of dyeing, which we can see in the next slides. We also have possibility of doing finishing along with dyeing. So when we are actually doing pre-coating of the dye onto the textile, we can also pre-coat the finishing chemicals along with the dye. And when supercritical CO2 is going to make the dyes penetrate inside, the finishing chemicals also can penetrate, and you can have even better bonding of the finishing chemicals with the textile material. Our batch times will be almost half as compared to the prior art CO2 process, and commercialization becomes easier because now we don't have to have the problems about heat transfer, mass transfer by taking the dye from one place to another. Now the dye is already present at every surface of the textile, and supercritical CO2 can very easily come in contact with the high surface area and have the dyeing done. So we have good consistency. Earlier, because if you ran the batch for 2 hours and if you run it for 3 hours, every time you are putting some dye onto the fabric. So depending on how much time and how many cycles you do, the shade depth will vary. But here now the shade depth is strictly depending on what is your recipe, and because it's already present on the fabric, your batch to batch variation is minimized. And for this, we received our patents in US as well as in India. And we are a proud indigenous Atmanirbhar technology today available for the world. And we will see in the next slides different applications which we have done already, like as I said, for polyester, for nylon, polyester cotton blends, cotton, and other types of materials, even like zipper tape made out of polyester and yarns. Now here, one example we can see about the efficiency of our process, where we took the recycled polyester and used the conventional dispersed dye called coralline from Colortex, and at 1.3% dye with respect to the weight of the fabric, we got a particular depth of the color, and the same dye on the same fabric was dyed by using conventional process, exhaust process, at a lab with Colortex, and we saw that we got much lesser depth with the same dye, with the same concentration, and with the conventional CO2 process, the prior art process also they tried, and they got around 18 to 24% lighter depth in the shade. So as compared to our sample, we got around 18 to 24% less depth with the conventional process. But here you can see that even though we got higher depth, the first one is our sample, the second is with water dyeing, third one is with conventional CO2 dyeing. You can see that even with higher depth, we still got even better wash fastness. So the performance has not decreased, the efficiency has improved, and performance is also very good as compared to even the conventional process for which the dye was made. And similarly, we have done the testing with other fabrics, with labs. This is another interesting example where we have a fabric called Sarona, which was initially developed by DuPont. And this particular fabric has one monomer from, it's a polyester, but the one monomer is from the starch or a natural source. And here at DuPont lab, they use the dye-star dye, conventional Dionix dye, which is the dispersed dye. They had to use 3% concentration to get a particular shade. And we could use the same dye on the same fabric, but with 2.1%, we got similar shade. So that also shows the efficiency of our process. And when they tested the performance, that is the rubbing fastness and the wash fastness, they found that it was comparable and excellent to as compared to the conventional process also. So, and as I said, we have done other types of textile materials like zipper tape and yarn. This is a microdenier fabric from polyester where the high surface area due to microdenier nature of the yarn, it is difficult to dye in conventional method, and they have to use high quality dyes. And here we can see that we have used a very normal type of dye from a company called Spectrum, and still we could achieve a very good uniformity in dyeing because of our process. This is 100% cotton, which is dyed without using any salt. This is polyester cotton blend with different proportions of polyester and cotton. And here, what we are able to achieve is to have single step dyeing. That means we don't have to, in conventional process, we do dyeing of polyester part first, then we do reduction clearing, and then we do dyeing of cotton part by using salt, and then we do the washing. So it involves 2 steps and more chemicals. And with our Supra Uno process for polyester cotton or cotton polyester, we can, or viscose, we can use single step dyeing. So we were part of Fashion for Good innovation program. And through this particular innovative program, we were introduced to different brands and different textile mills who gave us the task of demonstrating the technology for their products. So Adidas had given us a fabric which had 70% cotton and 30% polyester, and they gave us the swatch from their conventional supplier who was following the 2-step process, as I explained, to dye the polyester first and then doing reduction clearing and doing cellulosic dyeing with salt. And they gave us the requirement of a particular performance in terms of washing fastness. And we could actually use the conventional dyes. These are the dispersed dyes from Dystar, and these are the reactive dyes from Dystar. We used it in single step, all the 6 dyes together, without any reduction clearing in between, because it's a single step process, and without using any salt. And we could match the shade and we could match the performance. And it's not specific to a particular dye. We could achieve the same results by using Huntsman dyes. These are the dispersed dyes and the reactive dyes. And for a particular recipe, we could achieve the results with a different recipe also. Similarly, for the same project, we got a sample from PVH, which is another brand, and they gave us a cotton polyester blend with elastane, 5% elastane from their supplier, which was with 2-step process. And we could again match the shade and the performance in a single step. Just to give you an idea, here it might be taking 8 to 12 hours with a lot of chemicals, and here we are taking not even 2 hours, and we are able to get it in single step. So again, here we did the work again with Huntsman dyes to show the flexibility of our process, that we don't require any special dyes as such, and we are using the same dyes.
Dr. Baser?
Yeah.
Dr. Baser, I'm sorry to interrupt you. I am sure, I don't know how long your presentation is, but there would be questions. We'd like to give some opportunities for questions. So if we can.
So give me 10 minutes. In 10 minutes, I'll finish. Right. Is it okay?
All right.
Okay. So basically we have, this is an example of cotton dyeing, where we have used the conventional dyes, reactive dyes from Huntsman. And this particular column here shows different shades by a particular recipe. And here they have used salt and conventional exhaust dyeing. We use the same recipe, but with supercritical CO2 without salt, and we could achieve equivalent shades and we could get equivalent performance as well. We have done some life cycle analysis. We compared our process with the conventional beam dyeing process, because we also make a beam and put it into supercritical CO2 dyeing vessel. So if you compare it with the conventional beam dyeing process, we can see that in the conventional process, you have more number of steps. So it takes longer time. We take shorter time. Where there are more number of chemicals going in. We have less chemicals. And in conclusion, you can see that the reduction in impact in terms of water-based dyeing, we have 78% reduction for water, 40% for electricity, 69% for steam, for auxiliary chemicals, for wastewater, there is a significant reduction. For polyester cotton, as I said, these are the conventional methods for exhaust dyeing with two-step, pad dry, thermosol, pad steam with conventional for 2 steps. And this is Super Uno with single step. We are actually reducing the chemicals tremendously. So if you see here, we are using as much as 90% less chemicals for polyester cotton blends. We are using 51% less energy, 77% less water, 70% less time. And when you compare the cost of production, when we compare the cost of chemicals, utilities, water treatment and fixed cost, because we are saving good amount of chemicals, our process Supra Uno is not very expensive, so that the user can still give the product at similar cost even after using a highly sustainable process. And this is not for zero liquid discharge, this is normal processing. But if you go for zero liquid discharge, which is the requirement today, the cost of effluent treatment will even go up, and then it will become even more attractive because we have 90% less chemicals to start with. So in conclusion, I can say that we have a very versatile, simple, sustainable and economical process, and we actually can genuinely reduce the chemical pollution and use of water and saving on energy using the process as I have explained. Basically, this is what I had to say. Just to conclude, we have received few awards along the way since last 25 years, and this is something very dear to our heart and very proud to have received at the hands of Dr. Abdul Kalam for our technology day. Thank you.
Congratulations. That seems you're really on the right path, Dr. Baser. There are a few questions lined up. So if I can, if you have caught your breath and had a cup of water, I'd like to start with the first question from Arya Deshpande. So she has a question. What is finishing during dyeing?
So it is moisture management. For polyester, as we know, polyester is a hydrophobic material. And for you to have a comfort, you want the sweat to be absorbed like cotton. So they use, it is like wicking property. So they use chemicals to coat the polyester so that the moisture absorption is improved. So that is normally done after dyeing. So after dyeing is done, they coat the dyed fabric after washing and with the moisture management chemical and then dry it. But with our process, we are going to add both the dyes and moisture management chemical together. And here the supercritical CO2 will have chance to even make it penetrate. The earlier process, it will just be on the surface. So after a few washes, it may go off. Here you will have more efficiency of the process. So we not only save the time of a single second step, but also the energy and even better performance.
Right. So thank you so much. Mr. Ajit Lakra from Ludhiana. Would you like to please ask your question? Mr. Ajit Lakra, please unmute yourself and go ahead and ask your question. Are you around? Okay. Maybe we can wait a little while. So in the meantime, Mr. Amit Jain has a question. The critical part of this seems to be layering the fabric with dye. Where is this done?
So it is basically, we can use any process today for very uniform coating of the dye solution onto the fabric. We can use a very time-tested material process like padding, like as we do it in fold pad batch or continuous processing. Also, nowadays we can use spray. So now there are people who have developed very uniform spraying of the solution onto the textile to get very uniform coat. We have even used for checking purpose inkjet printing. So you use inkjet is again nothing but spray. So to have a very uniform coat, and so irrespective of what process we use for pre-coating, as long as it is uniform and controlled, we are successfully doing the dyeing as a next step. Thank you.
Right. I am sure.
Ajit Lakra has written that he is not able to unmute himself. Perhaps.
All right. So yes, we can read out the question he's put here. So Ajit Lakra asks, do we have the same conventional dyeing vessels in this technology, or they are different? If
Right.
different, then what is the cost and availability as per capacity?
Absolutely. So they definitely are different, because here, as I said, we have to go above the critical pressure. So critical pressure is around 74 atmospheres. In the conventional method, we go typically 3 to 4 atmospheres for our water-based dyeing. So we will need high pressure vessels for supercritical carbon dioxide based processing. We are actually a company who supplies the supercritical fluid processing equipment for the last 25 years. So the same will be supplied by us. So the pre-treatment can be done in a conventional way, and post-treatment can be done in a conventional way. It is the dyeing, waterless dyeing will be done in a different way with supercritical carbon dioxide, for which we will require special equipment. But it can be, it is very fast. So the size of the equipment is the efficiency of the process makes the equipment quite compact. For around 4 tons per day processing or dyeing of fabric, it can be housed in an area of around 30 feet by 20 feet and in a room of say 50 feet by 50 feet. So that is the compactness because of the efficiency of the process. The cost will depend on the size, but typically for around 4 tons per day, it will be around 1.6 million US dollars. But let me tell you that as compared to the other prior art CO2 technology, which is only limited to polyester, but because of less efficiency there, their equipment cost is almost double as compared to what we are talking about. So when we talk about the cost of production, the cost of investment is only one part, which was the fixed cost, which I showed you in the graph. But the saving on the other parts actually makes the technology very competitive per kg of fabric calculation.
Right, sir. So another question from Mr. Kumar. Many industries adopted soft flow machine operation. How much capital cost is needed to in investment and adopt this whole process for minimum 500 kg machine?
Right. So basically, because it's a high pressure process, so actually what happens, in soft flow, we define based on the volume, that's a 500 kg machine, because it will take longer time for each batch. Whereas here we actually would like to term it in terms of dyeing capacity per day, so that, it becomes apple to apple comparison. So as I said, for 4 tons per day, the investment will be close to around 15-16 crores, including the pre-treatment and post-treatment machines. Just for the supercritical CO2, it will be around 12.5 crores.
Right. Mr. Bajpai is asking, spray of dyes and finishing agent seems most critical in your innovation. So can you elaborate on that, please?
Absolutely. So we are doing this particular spreading of the material on the entire surface in a very uniform way, so that the uniformity and efficiency of dyeing is assured. And but because it is we are using similar machines, same machines. Like for example, today CPB has become very popular. CPB has been adopted for 100% polyester, but CPB is only suitable for for 100% cotton. So CPB is only possible only for cotton. Whereas now the same machine for pre-coating we can use, and when we club it with our Supra-Uno process, we can use it not only for cotton, but also for polyester cotton blends, for nylon, for acrylic, wool, etc. So the coating process is very well developed. That machine is not going to be made by us. We are going to use the good quality machines which have been developed over the years as a pre-treatment, which can be taken by the user themselves, or if they have existing machine, we can use the same. It's only the supercritical CO2 dyeing machine which is going to be added extra.
Right. So there are some very direct
questions. Can I ask, ma'am?
Yes, sir. Yes, sir. Yes, Mr.
Sir,
yes.
my one question is that what is on an average cost of production in your technology compared to the conventional one, just on an average?
Right, sir. So can you see this graph on the screen?
Yes.
So this is the cost of production, which we have calculated for exhaust dyeing, which is the conventional, the first one. The second is for pad dry thermosol pad steam. And the third one is for Supra-Uno. So you see here, because we are talking about comparison, so we have considered the same amount of cost for the given chemical, for the steam, or for any other material, water, so that, you know, it is just a comparison. It can be either 90 rupees or it can be 110 rupees, but it depends on, so apple to apple comparison, you can see that the cost of production is not very high as compared to the conventional process, primarily because we are saving on the chemicals, we are saving on water, we are saving on effluent treatment costs because of less chemicals and less water.
That's my question, is that how much percentage, supposing in conventional is 100 rupees, in your technology it is 50, 60, 40, how much is that?
Here, if you see this is like 90, 95 rupees for conventional, and for us it is around 65 rupees.
65.
But
okay,
sir, let me add that it is definitely desirable to have a better technology at a cheaper rate. That is the ideal situation. But as I told you, the plants working in the world with supercritical CO2 technology, with the limitation of only polyester and with only specific dyes, special dyes, the cost is much, much higher when they are getting it dyed, because the sustainability is important. Today, now with our indigenous technology, we are not, it's a world-class technology, but today the adoption of a sustainable technology becomes easier, because if we do not ask for higher price from our ultimate customer and give him a better product, that is what everybody is looking for. So I think we can meet that requirement.
So just one more question. You know, Ludhiana is a textile city, and the most of the units are in the MSME category.
Correct.
There are very few who are large units.
Right.
That means the capital cost of your machine seems to be very high. In the conventional machines, there are a number of manufacturers and we can select any good machine.
Right.
But here it is a kind of monopoly of yours only. We cannot select any more machine. So is there any chance of reducing the capital cost of the machines?
Right, sir. Let me put it in perspective. Like, we are in the same world as everybody else. Now, as I'm telling, as on today, the other supercritical CO2 technology is almost double the price. Okay. And here already we are offering a much better technology. Not apart from polyester, we can do all other fabrics. We are using conventional dyes. We are doing one step polyester cotton dyeing and all that at half the price. And it's a world-class equipment. Our oldest commercial plant is running for last 22 years. That actually speaks for the engineering. So already we have been able to, because of the improvement in the efficiency, we have been able to make it compact and it becomes more viable. Now, if something better can be possible, definitely we'll do it. But it is very important for us to do it at the world-class level, and try to give it at the best price. So already we have done it at half the price as compared to
Okay,
anybody
now
else.
my last question, sir, if you allow me. You
Yes.
know, I from Ludhiana, I offer myself to be the first to install your technology. So I would like to put up one machine, maybe of 400, 500 kilo capacity. For my point is that, is it scalable later if I am satisfied? And for the first one, I'll be able to show it to any of your prospective customers here. It's a very big potential market.
Yeah.
So I would like to have some special concession as a first buyer from Ludhiana. So your comments
Welcome,
about
sir.
this.
We definitely see. I respect what you are saying, and for the same reason, we have been doing trials for the industry for last 3 years. As I said, we have done more than 1,000 trials, and today, you know, a lot of industry is very happy with the results what they got, because what we do is we take your fabric, we take your dyes, we take your trichrome recipe, and do it without using water. So you get exactly apple to apple comparison. If I use some other dye, I use some other fabric, you will not know what I'm doing. So you're welcome. We are always open. We are here. You can see our background. For last 30 years, we have invested for all state-of-the-art technologies. So when I started at IIT Bombay, when we started this company, we got a lot of awards, but no purchase order. So we have to we have the experience of making the technology successful. Our commercial scale plants are running for last 20 years.
No doubt a wonderful technology, and this is going to create a revolution, because in Punjab, in Ludhiana, we are in the black zone of water.
Correct.
So water has become a very big problem. The treatment as well as the availability of groundwater also is a big problem.
Absolutely.
You will be doing a great service to the country, to the nation, to the society as well, I'm sure.
So the government of India, our textile commissioner, madam, Mrs. Roop Rashi, and even we had a small meeting with our minister and the secretaries. Everybody is very supportive. Even Invest India people are very supportive. So I think to have a good model of investment and to go ahead, it will not be a problem, sir. I have seen, I have never been abroad for job as others go. And I have seen that in India, there is no dearth of funds if your intentions are correct. And you can put your things and there is no problem. And today,
any carbon credits available in this technology?
I'm sure there will be, because you are reducing on chemicals, you are reducing on water, you are reducing on energy. It will be there, of course.
I think you should verify and put it in your agenda, because carbon credits.
I think, Mr.
give
Lakra, you can
benefits.
have one-to-one discussion.
Yeah.
You may have one-to-one discussion with Dr. Baser later on.
Okay, thank you.
I will provide you his number, and you can talk in detail.
It was heading towards another topic altogether, and a very big topic. It would have been wonderful if we have more time, but there are just few more questions. Would you like to take them, or?
Yeah, sure.
Okay, there's a question on, is there any possibility of implementing this technology in existing machines?
Right. So as I explained that if somebody has the existing CPV plant, we can use the same for pre-coating, and the existing washing plant because after the dyeing, very small amount of unfixed dye will be there on the fabric, which has to be washed. So those facilities can be used as it is. It is only the dyeing, waterless dyeing, which has to be added to the facility.
Right. And what would be the difference between cold pad batch, continuous dyeing method, and patent SCCO2 method? In continuous method for fixation, steam is used.
Correct.
Here SCCO2 with high investments cost.
Right.
It's right. So this question is from Kumar.
Right.
Kumar, if you'd like to elaborate.
No, I think I can answer that question maybe. And then if something is remaining, see, basically for that reason, this particular graph is drawn. This is for pad dry thermosol pad steam method, which Mr. Kumar is referring to, where they do the padding and then they do 2 times padding and then 2 times drying, steam with one place they use steam and other place they just dry it. So this is the continuous process, which is very high speed, which goes at around 40 to 50 meters per minute. And here the exhaust process is a batch process, as well as supercritical CO2 process is batch process. Even though ours is a batch process, we are still able to compete in terms of cost of production, because the efficiency is good. So,
Right.
and the cost of chemicals are low for polyester cotton blend here specifically. So I would say that with apple to apple comparison also, we are not very off. We have much better advantages and genuinely sustainable, compliant, and we can compete with the existing zero liquid discharge companies. We can't compete with somebody who is throwing his waste into gutter. We can compete with people who have zero liquid discharge, so that they are compliant.
Right. So one more question from Maral Sarovar. Please go ahead, Mr. Maral. Unmute yourself, please.
The dyes has to be put on the fabric first on CPB machine.
Yeah.
Then CPB machine is already capable of dyeing. So will it not be an additional process in that case?
That is what you're saying is correct, sir. For only cotton, 100% cotton only can be done on CPB. But CPB also has one more problem, that you have to do it for around 12 to 14, 16 hours. It has to be kept. Whereas after coating, our machine will not take more than 1.5 hours for the completion of process. So one is, it is very efficient, and for 100% cotton, definitely CPB is a very good process. But apart from 100% cotton on CPB, nothing else can be done. For that, our process is really versatile. You can do all other types of fabrics, and also finishing along with the dyeing, which also will not be possible in CPB.
So when we compare the cost comparison in your graph,
right?
If I go in CPB method, then after CPB spreading of shade or dyeing,
right,
we can, after waiting for some time, we can go straight in the finishing process.
Right.
So in that case, how will we save cost if we have to have?
Agreed. So as far as CPB is concerned, for 100% cotton, definitely it is one of the good technologies.
We will
So
not have any cost in that case if we are a 100% cotton company.
Can you please repeat?
If we are in a 100% cotton dyeing company,
right,
and we have CPB,
yes,
and do we save anything in terms of dyeing?
I would, yeah. Means actually, CPB, all said and done, is not very popular. There are some limitations and there are some issues. So if you're comfortable with that, it's definitely a good process. I have also heard that they use silicates. People claim that they have some substitute, but ultimately silicates are again a main problem for environment. So I would say that for any process, there are number of routes. We have to look at the complete picture when we want to compare. For a particular fabric, for a particular shade, something may be more advantageous. But when we are talking about sustainable technology for India, it should have the kind of flexibility, it should have the kind of reach and the competence to handle the maximum possible things. Because today, pure cotton is going to have challenges in terms of cost. So I think we should have technology which can also handle polyester cotton, polyester viscose, and other fabrics.
Sir, I have one last question for you.
One minute.
Sir, I have to move on, please. We may take it later, but Mr. Labish Kumar has been posting question on question. I've not been able to give him a chance. So I'm going to read it out. How is the dye affinity issue resolved compared to prior art process? Can you help elaborate to explain it?
Yeah. So basically, as I said, the main issue was about the contact time, contact area, and the solubility of the dye. So by our process, we have been able to kind of solve it really efficiently. As you can see in the results, that the dyeing efficiency is better, the wash fastness is comparable or better. So that is how, and very importantly, the conventional knowledge about the stability of the dye was because with the earlier processes with water. So in the earlier process, what happens is you have water, you have oxygen, you have heat. So when you have water, oxygen, and heat together, along with the textile and other materials, there is a different kind of chemical reaction which may happen. With supercritical carbon dioxide, with our supra-Uno process, there is no water, there is no oxygen, and with that, we have seen that the carbon dioxide doesn't react with anything. So we have seen that the efficiency may be increasing because of the less degradation of the dye and less degradation of the textile and other things. So this is a completely new chemistry which has come up, and thank God we are only chemical engineers, not chemists. If I knew more chemistry, I wouldn't have tried this. So it always sometimes helps you to try things rather than just going by the book, you know. And we have been able to develop.
Thank you, sir. Thank you.
Dr. Baser, one moment.
Yes,
Dr.
sir.
Baser, I think people are very curious about discussing with you.
Yeah.
Can we share your mobile number here on the screen?
Absolutely, please share. And otherwise, even suprauno.com is our website. So I would request them to go to suprauno.com. Here I can show you at the bottom. The mobile number is also there. You are welcome. We are definitely putting all our efforts and energy for the industry, and we are most happy. You are welcome to visit us anytime you are in Bombay to see different samples. We have a lot of samples to show you, and we can do trials for you. And I'm really happy today. Mr. Ajit Lakra also said that they would like to be the first one. I am definitely with everybody. We are already talking to a good amount of industries, and
Thank you, sir.
and the government is very supportive. So let us, I would say through NISTI, I would like to say that a lot of investment is planned from government, like PM Mitra Park, and a lot of common facilities are being planned. A lot of things are being planned in India. Now we have the opportunity to use that money right way. So we should really focus on sustainable so that it doesn't become liability, it becomes an asset.
Thank you. Thank you, Dr. Baser. I think all our participants here are going to be really happy connecting with you. I am going to now invite Dr. Kushal Sen to summarize the conversation today and to give your expert comments.
Thank you very much. It's been a very productive evening. I'm sure Dr. Baser would be satisfied with the kind of questions that people have been asking. It's really been technical questions, and of course there are marketing and other cost-based questions also. There is no doubt that whatever you are doing is a good one. I'm just wondering, and what will be the time frame where nobody will ask these questions. They will start using their your technology and the machines, and hopefully all the processes sustainable. So as I understand is the most of the process, as you call the pre-padding process, where you actually pad or apply, generally padding anyway is a known process. So you are hopefully, other than dye, maybe you are adding some chemicals also along with it during
very few, like dispersing agent, leveling agent, anti-migration agent, but we are not using any salt or any other material which is really in big quantity.
So what I understand is alkali maybe you're using for dispersed dye, direct reactive dye.
For reactive dye, yes, we use alkali.
So it's like, you know, some pre-processes which are required for a particular dye. Obviously, the dye which is dispersed type of a dye is going to be dissolved, also solubilized, and then it will be moved in. But the padding process for the reactive dye, which obviously must have in aqueous solution, so therefore it's already gone in during the padding. So as far as that process is not concerned, process as far as the penetration is concerned is not an issue. Fixation is one thing which somebody has to understand. Maybe if you want to, sometime want to elaborate on it, because generally, obviously, you have alkali, so it is being, fixed by that and whatever it is. So it's a very nice process. And if you say some of the some finishing agents also can be applied, which can probably, react, or because it's a pre-padding process, so you can always choose certain chemicals which can obviously make sure that it reacts. It's a very nice process, and I'm very happy that you have done it. And I'm just also hoping that the industry comes out and at least starts putting up their plans, because after all, somebody has to start. I don't know, because you said 1,000 trials you have already taken. And so we wish you a success, maybe through Ludhiana or any other areas, and let there be some demonstrable, not just your slides and your thing, that actually somebody is using and they have their own results, and they will have their own problems also, which they will come to you and you will try and solve the problems as well. So I think wish you really good luck, and your company. We need people like you and your company, so that indigenous processes, indigenous technologies are promoted. It's a world-class technology. You are already an expert, as you said, from 25 years you've been using supercritical carbon dioxide. And so I'm quite sure the time is just ripe, I must say that. The threshold has already come, and people will start using some of the things. Once you have a few customers, their certificate is what's going to make that happen. And I'll just advise in one way that you might like to use an independent organization to evaluate your process from energy, chemicals, and other point of view, because otherwise everybody obviously wants to promote their own ways, but there may be different ways of looking at the sustainability.
So Fashion for Good was one platform where everything was evaluated, because Fashion for Good is a Netherlands-based NGO, which is promoted by all the textile mills and the brands. And so they had this, they gave us an opportunity where we did this life cycle analysis, and we could actually prove that it is workable.
That's the best, so your certificate comes from the user as well as an independent agency.
Absolutely.
Who are not promoting you. They're just wanting to look at the technology in a critical way. It's always better to have a correct feedback to met the technology. You are a scientist. I'm very happy that you have started your educational, at least the postgraduate stuff from IIT Delhi.
Yeah.
So I hope we have contributed something.
From the same building, sir. From the same building.
Same building. The building is still the same, it's still to fall down. We're waiting for that.
Right.
All the best, and thank you very much. And I'm very happy that NIST is actually picking up such type of events. All the best.
Thank you, Dr. Kushal Sen. And at the end, but not the least, I'd like to invite Dr. Bajpai to give the vote of thanks.
Good evening, everyone. On the eve of Independence Day, on behalf of NIST, I am glad to be here to express my thanks. I would like to extend my thanks to Dr. Baser for sharing his innovative technology knowledge of supercritical flow and waterless dyeing. NIST put all efforts to provide platform for knowledge sharing among textile professionals. Our chairman, Dr. R.A. Lal, is generous with time and keep motivate to all NIST teams. My sincere thanks to Dr. Yadav, Professor Neon, Professor Kushal Sen to handle this webinar very successful. My sincere thanks to all participants who joined us and make this webinar successful. Thank you one and all being here and make successful this NIST seminar. Thank you.
At the end, I would like to express my gratitude to Dr. Vijay Yadav, Professor Neon, Dr. Shanbag, Mr. Bajpai, and all whole NIST team. Thank you all.